So the next exercise is number 14. Here we have a positive integer k greater than or equal to 2. That means k is any positive integer which is not 1. It's greater than 1. Then we have to prove each of the following. We are seeing part A here. We will see parts B and C afterwards. So in part A, another integer n is given in terms of k. This is 2 to the power k minus 1. And then we have to prove that it satisfies this equation, that the sigma value of n would be 2n minus 1. So let's first solve this. So the solution is pretty straightforward. Because of the structure of n, we are immediately able to apply our formula for sigma. N is itself a prime power. That means only one prime divides n, and which is 2 in this case. So according to our known formula, because there is only one prime factor, so there will be only one term like this. Had there been other prime factors, other such terms would have appeared here. But anyway, so what shall we have here? 2 to the power k minus 1. So think of this n as p1 to the power k1. Here p1 is 2 and k1 is k minus 1. So the formula was then p1 to the power k1 plus 1 minus 1 divided by p1 minus 1. So that way we get this. And the denominator is very convenient, it becomes 1. So we end up having this, because this minus 1 and plus 1 will cancel each other. And that way we get 2 to the power k minus 1. Now you can write this 2 to the power k as 2 times 2 to the power k minus 1. This, however, is just your n. So that's how you get 2n minus 1. So that is part A. Now next let us see part B. In part B, our n is not this 2 to the power k minus 1, but instead something else is given. This number is prime, and this is our n, 2 to the power k minus 1 times this one. So we are being asked to show that this n satisfies this equation, that its sigma value would be twice its original value. So I have written the solution on that side because it involves such a calculation. So it's a little weird to start from here. So here also we straight away go for sigma of n. So our n is this number. Now how are we instantly able to write the sigma value like this? I mean, are we looking at a prime factorization? Yes, we are looking at the prime factorization of n. How exactly? Well, this is 1 power of the prime 2 that divides n. The power is gone. But anyway, so what about the other factor? The other factor is 2 to the power k minus 1. Now it's already given that this is also prime. However, how do we know that this prime is different from 2? Well, that is simple. No. 2 is the only even prime. This number, however, due to its structure is odd. It is not even. It's not divisible by 2 because of this minus 1. And because of the fact that this 2 to the power k is divisible by 2. That is why this is actually a prime factorization, the prime factorization of n. And so the sigma value of this number looks like this, where we see one term in this product for each prime. For the prime 2, obviously this comes just like the previous one. And for this prime, what will come? Note carefully that you have to treat this entire thing. Treat means it is actually a prime. So what we are looking at here is the prime factorization of n, which has this form p1 to the power k1. p1 is 2, k1 is k minus 1 times p2 to the power k2. p2 is this entire 2 to the k minus 1 and k2 is 1 because here there is nothing, no higher exponent is there. So that is why, and then what will happen for this prime? For this prime you will have p2 to the power k2 plus 1, because k2 is 1, k2 plus 1 is 2. minus 1 divided by P2 minus 1. And you already know what this will become. This becomes 2 to the power k minus 1. However, what did we do here? Here we applied our familiar formula a square minus b square. In its place you can write a plus b times a minus b, and then that a minus b and a minus b will cancel out, leaving you with a plus b. But what does this become? It becomes 2 to the power k. Now you can write 2 to the power k as 2 times 2 to the power k minus 1. And if you look at this, this is just your original number. So you write n here, and that's how sigma of n equals 2n. So this is part B, and then there is part C next. Part C is also similar. This time it is given that 2 to the power k minus 3 is the prime, and the number is 2 to the power k minus 1 times this 2 to the power k minus 3. And for this n we have to prove that it satisfies this equation, that its sigma value is its double plus 2. So let's see the solution. Because this one is similar to part B, so it makes sense that I modify the previous one here. So from here I start the solution. Everything is similar, only now we have 2 to the power k minus 3. So accordingly its sigma value is this. Now you already know why this comes. So this as before becomes 2 to the power k minus 1, and this one becomes 2 to the power k minus 3 plus 1, the prime plus 1. So now however we are not going to get 2 to the power k only from here. Instead we get 2 to the power k minus 2, and this one stays here. Recall that previously this became 2 to the power k, so we wrote it on this side. But anyway, so now if we do the multiplication, what are we going to get? 2 to the power k times 2 to the power k is 2 to the 2k. 2 to the k times minus 2 is minus 2 times 2 to the k, and another minus 2 to the k. So that is minus 3 times 2 to the kth power. Minus 1 times minus 2 is plus 2. Now you can write this quantity, this number like this. Plus 2 you keep as it is separately, and in place of this first two terms you write this. Is it going to be equal to that? Let's see. If you do the multiplication, here you have 1, 2, and here you have 2 to the minus 1, so they cancel each other, and you are left with a 2 to the k and another 1. So they together really give you 2 to the 2k, 2kth power. And of course this times minus 3 is minus 3 times, this is, if you do the multiplication, it is 2 to the kth power, and plus 2. Now this thing is actually just your original number, so that way you get 2n plus 2. So that's the solution to part C. So this completes this exercise, and let's see another one. Next, the 16th one also has actually two parts. This is the first one. For any integer n greater than 1, we have to prove that there exist integers n1 and n2, such that if you add their tau values up, then you are going to get n. So let's first solve this. Well, the solution is pretty easy. If you use exercise 11, we didn't solve this exercise 11, but if you go and see its statement, you will understand how we are using it here. So by exercise 11, n minus 1 would be equal to tau of n1 for some positive integer n1. Actually, this exercise tells us about the existence of infinitely many such positive integers for which the tau value would be this given n minus 1. Note one more thing, that you are able to apply this exercise because n minus 1 is a positive integer itself because of this inequality. So now with this fact, it's pretty easy to express n like this, and that is just this. In place of n, you write n minus 1 plus 1, and then you write tau of n1 in place of n minus 1, and you already know that tau of 1 is equal to 1. So one of those positive integers is this n1 and the other one is 1, that means n2 is 1 in this case. I am not saying that this is the only way of writing n, but we just want to show that there exists at least one such representation of n as a sum of two tau values. So that's it, that's the solution to part A. Next let us see part B. So this is part B, but before we see part B, let me just address something which may be bothering you. Maybe you think of this sometimes. How do you know, how do you figure out that here you would need exercise 11? See, very rarely, it happens very rarely in a textbook that if a set of exercises is given to you, that the exercises are standalone, that they do not have anything to do with the other exercises. Usually, this is a sign of a good book. The sign is that the exercises are actually interconnected. That if you solve one of them, it will help you solve some others. And then a few of them which you solved initially, they will help you solve something else. Okay, so that's how it just builds on top of itself. It's not like each exercise is erecting itself. I mean, when you find its solution on its own and it has nothing to do with the other exercises, it's not like that. So that is why you should keep an eye out for, you keep searching what may work, what might work in a given solution. So existence of such an n whose tau value is a given integer, that is there in exercise 11 statement. So I thought of somehow trying to use it here to solve this one, and it worked. It does not always work, okay. You have to keep on trying new and new ideas. Something will click and sometimes something may not click. Okay, so that's how it goes. It's always a trial and error process. So let us next see part B. What do we have to prove here? Here we have to prove that the Goldbach conjecture, which itself is unsolved, we already know. But if you assume that the Goldbach conjecture is true, then using it, you can now show this, that for each even positive integer, because it's even, it's going to look like 2n for some positive integer n. There exist integers n1 and n2, but this time, this happens, that the sum of their sigma values equals 2n. So how can we solve this? Let's see. In the beginning of the solution itself, we dispose of some easy cases. These three first easy cases. The first case is when our n is equal to 1. In that case, 2n is 2. Now you can write 2 as 1 plus 1, of course. And then 1 is sigma of 1 and 1 is sigma of 1. So that way you are able to write 2 as the sum of two sigma values of some positive integers, in this case, which are both equal to 1. And then the next case is when n is equal to 2. So 2n is 4 and 4 can be written as 1 plus 3. 1 is sigma of 1 and 3 is sigma of 2. Because 2 is a prime, its only positive divisors are 1 and 2. And their sum is 3. So that is sigma of 3. And the next one is 6. Here n is 3. So 6 can be written as 3 plus 3, which is sigma of 2 plus sigma of 2. So that means the claim is true for these first three values of n, 1, 2 and 3. So now we can assume that our n is greater than 3. And this is where we are going to use Goldbach's conjecture. What form of the conjecture are we using? We are specifically using this claim that any positive integer which is even and greater than 4 can be written as a sum of two prime numbers. There exist two prime numbers for such an integer such that their sum is the given integer. And how have we used it here? There would exist primes p and q for which 2 times n minus 1 equals p plus q. Is 2 times n minus 1 an even integer? Yes, it is. Is it greater than 4? Let's see. N is greater than 3. So n minus 1 is greater than 2. Now if you multiply both sides, on both sides by 2, you get 2 times n minus 1 greater than 4. Yes, it is. So that's why we are able to apply Goldbach's conjecture here, and in that form of the conjecture. But then what happens? The left hand side is 2n minus 2. So if you add 2 to both sides, the left hand side would become 2n. And the right hand side would also get plus 2, which you can split like this, plus 1 plus 1. Now p plus 1 is sigma of p and q plus 1 is sigma of q. So that way, for this type of n's also, 2n is expressible as the sum of two sigma values. And that completes this solution. And let me end the video here itself. There are of course other exercises after this, which we will see next week. So see you next week with those things. Until then, this is me, Lucifer from a mathematical room. Have a nice day.